I'm Aaron Zweig. This is provably efficient third-person imitation from offline observation. It's a joint work with Joan Bruna at NYU. So the problem we're interested in is, say you have a source MDP, in this case Pong, and you have an expert policy who plays Pong very well. And you'd like to do what seems like a very simple transfer problem, which is move this expert policy so that it can play in a target domain, which is Pong, but all of the pixels are green. On the surface, this just seems very straightforward, but because the state spaces are different, i.e. some of the pixels are white in the source domain versus green in the target domain, you can't directly apply your policy. You have to do something else. So the way we formalize this problem is as isomorphic third-person imitation. So you have a source domain, which is some MDP, and you have your target MDP, which for simplicity, we assume they share an action space. The important point is their state spaces are totally different, and consequently their dynamics can be totally different. So the isomorphic assumption comes in the form that we assume there's a bijective mapping between the state spaces, so some pi star, that preserves the dynamics. So in other words, these are essentially the same MDP up to a relabeling of the states. So what is our goal here? It's an imitation problem. So we're going to assume that we know everything about the dynamics of the source MDP, and we have an expert policy that acts in the source MDP, some phi. And we want to figure out how to either transfer this policy or learn a different policy in the target domain that imitates this phi. So what imitation here means is, say you have some policy that acts in the target domain, and you're going to compare that against phi if it's perfectly transferred using pi star, the true bijection. And then once you have these two policies in the target domain, you're going to look at the total variation of their occupancy measures. So what are you allowed to understand about the target domain? So we consider two regimes here. In the offline setting, you don't get to play in the target domain at all. All you get to see is an expert who draws a few trajectories following their perfect policy in the target domain, and then from that information, you have to try to learn the bijection. In the online setting, you get to play in the target domain, you get to run whatever policy you like, but you never get to see what an expert would do there. So to give that context from our original example, in the offline setting, we have our source MDP, Pong with regular pixels, and we have an expert policy, and we never get to play in green Pong in our target domain. We only get to see 100 games, say, of an expert playing in green Pong. And from that, we have to somehow work out what the bijection between the state spaces in these two MDPs are. In the online setting, we don't get anything else from the expert. We're just in the target domain. We get to play green Pong and learn for ourselves about the dynamics. So we have two main results. For the offline setting, we have an upper bound based on algorithm to approximately learn this bijective mapping. And once you have an approximation of that bijective mapping, you can approximately map the expert from the source to the target. So in order for this to work, we have two main assumptions to make this feasible. So if you look at the expert's occupancy measure, you want to assume, first of all, that it's asymmetric, which for us, we encode that as you look at the Markov chain induced by the expert following the dynamics under that MDP. And then you want to assume that the singular values of that Markov chain are sufficiently separated. And the second assumption is that the expert's occupancy is concentrated in a small set. If the expert spends a lot of time in lots of various states all over the MDP, it's going to be really hard to learn this mapping. So under those assumptions, we get some nice guarantees. We get good sample complexity to achieve very small imitation loss between the true expert in the target domain and the policy that our algorithm produces. You have polynomial dependence on some underlying features of the MDP. But the important thing is you only have linear dependence on the size of the state space, which appears to be about as well as you can do using this total variation as your metric for measuring imitation. The online setting is much harder, so we just produce a fairly straightforward lower bound. The motivation here is that if you have a very symmetric argument or a very symmetric environment, it's going to be very difficult to learn what the true bijection is. Essentially, if you have your source and your target, and these are symmetric, there will be multiple possible bijections that seem to preserve the dynamics, and it'll be very hard to figure out which one is correct. So formally, we can show that you can reduce that problem in this online setting to determining the optimal arm of a two-armed bandit where the reward distributions are very similar, which means if you want to approach this problem in the future, you probably need to come up with more explicit constraints on how you measure this distributional distance between occupancy measures, that maybe total variation is too strong to get nice bounds here. Thanks for listening.